So greetings of the day. Today we are going to see 5G OTA and conductive more test environments. Okay. So in general, we'll have um, two kind of this for this is for FR1. Especially the OTA is for FR2 and FR1, but conductive especially is for FR1 alone because it cannot be done FR2 because see, if you go for FR2, then lambda will be very, it will be in 1 millimeter or lesser than that. So in that case, you will the components will be very tiny, and then we will not get those components, we will not get that many components available, and will be much costlier. So that's why, and also it is too much lossy because if, for example, if you are using conductive environment for FR2, you will get, end up in getting, a lot of losses because, for 1 meter cable, you will, because loss is directly proportional to the frequency. So it will be a plenty of losses. So that's why we normally don't use conductive environment in FR2. But OTA, in that case, so OTA will be a feasible one. So we'll discuss how it can be done. Okay, and these are all the outline of my presentation, frequency bands, and why. So why we generally go for measurements and various DOTs and measurements. So DOTs like node V and then onboard unit and mobiles, so something like that. Okay, measurement setup. So as usual, as said, conductor and OTA. It's actually basically not OTA. It's a radiated measurement setup, conductor radiated measurement setup, under which the OTA comes into picture. Okay. Then some of the measurement methods. So the far field, direct far field, indirect far field, near field, like that. Okay, and followed by summary. So I have referred mainly for this presentation mainly based on 38810, some of the online contents, but so in between we will also see 36508, so some of the setup details, and then 38801, and so some of the specs is been referred here and there. Okay, based on this only the presentation is moving on, and so now comes into picture. So radio waves, frequency bands. So frequency bands are categorized like this: radio waves, microwaves, infrared, visible light, and ultraviolet, X-rays, and gammas. So please do visit this website, what is spectrum, and ctia.org. It's openly available. So so it is very nicely presented, these bands and all. Okay. So we are working in microwaves. Okay. So based on this bands, so you see some of the bands being used for 5G or LTE or whatever it may be. So FR1 basically for 10 megahertz to 7125 megahertz, and then FR2 basically it's from 24.25 into subject to 52.60. But it will be, I think in release 16 or 17 it will be up to 77 gigahertz also. So earlier we used to call FR1 as sub 6 gigahertz, but it's no more valid now because it's being 7125 megahertz. And so these are all the different bands. I think we have discussed already in the previous presentation, and you can see here. So these are all the different sub-carrier spacing being used, and then these are all the 257, 258, 260, 261 band allocation. Okay, so based on that, and if you are going for ENDC, like OTA NR dual connectivity, then the combination of or carrier aggregation, the combination can be like something like this: N78 to N58 and N71 to N257. So something like this. So it will be it could be based on RF characteristics or some of the protocol characteristics or convenience. Okay, because you cannot have hardware to support maybe at a time these kind of things. So that's why based on hardware complexity and other things, they could have decided these carrier combinations. Okay, because for example, if you 257 and 258 you cannot have, because both are adjacent bands. Okay, so that they see here it's overlapping also. So what happens is you may not have a selectivity for the RF components. So that's why they could have chosen like this. Okay, so that's my assumption. Next, so why we go for basically testing measurement. So if you want to see testing measurements before the release of the product, for example, you are designing the product, and then your stack and everything is developed, and then you are we are if company is launching the product, so when it's get into market, so that time for example, if your product is not tested, what happens is, say, you don't know what component will function like what, we don't know. Okay, so we cannot just assume that okay, everything will work fine, so God's grace, then you just assembled and then launched. Okay, so as soon as even during the launch also might be working, so as soon as you launched, it is creating a lot of problems to the, it is working, maybe it is not working properly, or it is creating problems to the user, or it is creating problem to the environment, and then and so on. Okay, so that's why we, then after that you cannot, you have to come back and modify. It will take much time. So earlier and all, you will not have emulators and other things. So that's why what they will do is they will design the product, then realize, and then they will it will take much time. So now the simulation and the emulation is there. So we can design the product, and then the product cycle has become much narrower than the earlier. Because in earlier and all, you have to design the product, and not design the, so you will fabricate the product and test it. If you find defect, then you have to come back and then redesign that, or redesign and then fabricate again, testing. So it will take much time. But nowadays simulation is there, so you can realize your product almost like anything, and then you can even simulation itself, you can find out what is happening, and then you can design the product accordingly. And also next level of testing is there. So in that you can correct most of the your device performance, or node B, whatever it may be, any equipment for that matter. So you can correct as expected. And so there are certification bodies, so you cannot test as randomly. Okay, there is some of the bodies who had derived the testing methods, because like 3GPP, ITSE, and some of the regulatories, and for India it is I think department under DOT, there is one body is there for network itself. So what they will do is, see, these are all it's not a unique industry or anything. So it is an association of OEMs, so like original equipment manufacturers, and then chipset manufacturers, and then testing solution manufacturers like G-Site and other things. So like OEM, like Ericsson, Nokia, and so those people will come into picture, and then they formulate, and are also researchers, professors from eminent universities. So what they will do is, there will be a members of stakeholders of this 3GPP or ITSE or whatsoever. Okay, what they will do is, they will see what are all parameters to be measured before they launch the product. Okay, and what is that product, so description and everything, how to measure that one, then what parameter you have to, what results you have to get. So those things and all they will design, and then they will prepare a document, and each meeting they will keep on correcting. So that's what they call it as RAN meeting. So CAG meeting. So several meetings are available. So what they will do is, in that meeting they will correct whatever for example, some parameters is not being measured properly. Then later someone may propose that like CS, we call it a change request. Was that no, this is wrong, you have to be, it has to be like this. If they have a solid evidences, they will accept in the RAN meeting and then amend that. So first thing what they will do is, we have to be compliant. Like basic compliant like 3GPP or 8C. There are spec available in the open source 3GPP.org or 8C.org. So you can find out a lot of specs are available, and you can refer that. So a lot of specs. It's a huge amount of specs are available. RF in point of view, RRM point of view, protocol point of view. Okay. So why we need that? Because if in order to get certification, that your product can be launched in the commercial market. Okay, commercial or defense or civil market. So any market. Okay, for that matter. So some of the certification bodies, like GCF, and then Omniair, and etc. So some of the product certifiers are there. So what they will do is they will have a certain requirement. Okay, 3GPP, it's a commonly accepted basic criteria that is derived. Okay, some of the companies, some of the certification body may accept with the 3GPP alone. Some of the certification body may not accept because for example, Japan or some Korea or India, someone, so they will have their certain requirements on top of the 3GPP. Okay, so those required has to be met, otherwise your product will not be certified to sell in that particular country. Okay, so 3GPP is kind of basic requirement, minimum requirement. We can call it as minimum requirement. Okay, and so regulatory will be on top of the minimum requirement. They will set some of the stringent parameters, like it will not be much deviation from the 3GPP. For example, if your tolerance is, for example, you are setting it as plus 20 dB or minus 20 dB or something like that. Okay, and for some parameter, for some power parameter. Okay, then TRELEC or KCC, so the regulatories, what they will do is so they will set no, we cannot accept like this, so it should be plus 30 dB or minus 30 dB, something like that. Okay, so those corrections will be there, and some of the measurement technique they will say no, we cannot, you should not do like this, we have to do like this, you have to use this equipment and do this measurement, so something like that. Okay, and so first is the compliance testing. The second testing is that field trials. Okay, so once you are done with the testing at lab level, okay, so then they will go for field trials. So if you are claiming that your device will be working fine in the climate different scenarios and everything, they will go for field trials. So field trials means see it will be a more realistic one, because you will go to the field, and then it will be then they will set the node B. Say here you are emulating the node B and then using. There they will fix the real-time node B, and then they will monitor how real-time node B, and then they will monitor how UE is behaving in open environment. Okay, field trials. And then third one is interoperability testing. So interoperability testing means network consists of several equipments of different OEMs. Okay, so for example, someone will have node B, someone will have core system, MSC core system, and then someone will have a MME, so mobility management entity. Someone will have central unit, distribution unit, so something like that. Okay, so and UE will be different vendor. So it should be interoperable. Otherwise, it is no use, because earlier and all, if you are using one equipment, then it will support one certain thing only. Then came into picture that we cannot have one equipment for one equipment for one whole one network should not have should not necessarily have one vendor equipments. So then they came into picture and then say, okay, no. So that time only the interoperability testing was happened. Okay, because all will be as per some of the spec only. So whether UE or node B or whatever it may be, so common spec only they are going to follow. But still, so interoperability testing is mandatory. So once you are done with these three testings, then you can your product can be certified. Okay, and now even in advanced level they are going like open RAN. Okay, open RAN. So CU can be anything. So it's more of different vendors can play a role. Many vendors, plenty of vendors, even small companies also can play a role. they can add, they can integrate that their products in that open RAN network. So something like it is going on. Okay. And DUTs, what are DUTs we'll be using, we'll be testing, like Node B, UE, onboard unit. Onboard unit is especially for, CV2X, okay, or either autonomous cars applications. So onboard unit, okay. And measurement setups, so conductor mode, radiator mode. Conventional one is, it's a conventional power field setup, so one-to-one communication, and then we'll measure we will have a TX, some transmitting antenna will be there, and you will put your device and you can test it. So, but OTA is just something different. Okay, so it is imitating the real time scenario. And so as I said before, as we said before, like conductor mode can be used only for sub-millimeter wave frequencies, because as I mentioned, so components is much expensive, and then it is complex also. So handling also will be very difficult, because if you are not tightening, if you are tightening, for example, if you are writing with the hand, you are not applying some particular torque, then the connector will be broken from the cable. So that's also there. Okay. And also you cannot have a long cables, but in the real-time setup you should have a lot of cables, and then it will be a very tedious problem. So that's why we cannot use in millimeter waves conductor mode. Okay. And so it will be a too lossy, then you have to use power amplifier design also. So the cost will be very rapidly going up, and then customer will not that testing labs will not be preferring those things. So that's why they could have done this only for sub-millimeter wave, and then for a radiated mode for millimeter wave, and also for sub-millimeter wave. So measurement setup, first we will see conducted measurements. So in general, so what all equipments will be there, just we will see measurement will be there. One is Node B emulator or system simulator. Okay, it can be everything, like total system simulator. And then signal generator. Okay, signal generator is for what? So one maybe for in CV2X testing, we'll use for this for synchronization, GNSS synchronization, and somewhere we can use it for waveform generation and other things. Next, you will have a control PC or test PC, which will handle it will be like a coordinator. Then you will have DUT. Okay. So this is basically typically Qualcomm DUT and MDM9150. I got this picture from open source, you can see that. So DUT. So this will have this test PC and UXM will have both LAN connection and also signaling connection, and also MXZ. MXZ may not be having, only LAN connection it will have, because in order to control the parameters and in order to set the parameters during automated run. Okay, and these will have connections, and then these will also have connections. So here, so for example, this is the basics, a very basic setup. So UE, control PC, and network emulator, and then you will have a signal generator or something like that. But if you are, for example, if you are applying MIMO, you are testing MIMO. Okay, here 8 ports are available, but maybe some ports might be reserved for some other purpose. Okay, so in that case, so what you will do is, but you are testing 4x4 MIMO. That case we need additional network emulator. You can see that master and slave. Okay, and so master and slave. Okay, so master and slave. So what you can do is, this will become master, this will become slave. So what are additional ports you require to test MIMO, then you can use this, make use of these connections. Okay, and second and the third one more is that, this will also have a connection with the UE and test PC, and so through this master it will have a connection with the test PC. Okay, the other one is that signal generator. Okay, so this signal generator may not be for example, if you are this signal generator may not be applicable for beyond certain frequencies, then we have to use additional signal generators. Okay, for example, FR2 signal generator, for example. Okay, so that case we have to use this kind of signal generators. Okay, because for example, in some of the test cases, what you have to do is, you have to check the UE. You have to send the interference signal to the UE and certain frequencies, okay, and then check the performance of the UE, okay, or device or node B, whatever it may be. So in that case, how you have to send this waveforms, interferent waveforms from this signal generator. Next is important component is channel emulator, okay. Channel emulator, what they will do is, see, you will have a real time, you will have, different different environment, and my fading, scattering, multipath, everything will be there, okay. So that in order to emulate that, so we cannot have so many things within this box itself, okay. We have to offload some of the things, okay. For example, it will have basic fading scenarios, but we cannot have everything inside, okay. But that time, what you cannot have multi-port fading also, so you cannot create it. See here, what you can emulate is like for example, if a UE is moving the speed, what will be the fading and the multipath and the scattering. So those kind of stuffs will be embedded with these channel emulators. Then what they will do is, you can connect the UE, connect the UXM through this one, and then you can emulate whatever scenario you want, okay. But it is not arbitrary, so there are channel models are available. So this particular channel emulator will support certain channel models. So if your spec comply, if your spec says that can be used, then you can use that one. Otherwise, they will embed another channel models. That's all, okay. And so next is signal analyzer or spectrum analyzer, or whatever it means, okay. So signal analyzer, so this is the additional signal analyzer. It's within this box, there will be some signal analyzer, but limited frequency range. But in order to have additional frequency signal analyzer, you can use this additional one. And so this is this picture all I have taken from keysite.com, okay. So taken from keysite.com, and you can find it in R&S and R&D. So there will be different, names will be different, but so most probably it will be same. The components will be same, okay. And then you cannot assemble like this, right? You can see the zigzag connections. So you have to put into a certain fashion. So that's why they are putting in this box. So they are arranging in a certain fashion, and then through switching unit they will connect all these components, okay. And you can see that. So next we will see these are all the overview of the different equipments being used, okay. Next, channel models. Just now we have said that. So channel emulator is there. So there are number of channel models are available in 38901. So channel model frequencies from 0.5 to 100 gigahertz. So METAS, so WEBA, and millimeter wave evolution of backhaul and access. So ITR and so cost, so everything. New York University wireless. So they have proposed some of the channel models. So Fraunhofer, everything. Okay. So channel models basically, see how they will find is that, see how they will arrive at channel model is that, for example, in a city you will have buildings and trees and humans, and then cars are moving. So many things will be there. Okay. That they have to emulate the scenario. Okay. If your building is there, what will be this multipath effect and fading effect and scattering effect, okay. So due to which what path loss it will occur. So those things and all we have to predict in advance. Otherwise, you cannot design the UE in order to get, okay, if these scenarios are there, then how UE will behave. So those kind of tolerance is already been defined in these specs and all. Okay, if this model is applied, then you will have this many things. Okay, this is for emulation purpose only. That's just before we have shared that. Okay, compliance testing. Okay, but field trials will replicate that only. So field trials you can see actual scenarios. So you can find whether UE or device, whatever it may be, it's working properly or not. Okay, field trials will ensure that whether this because these models and all, they based on field trials only. So how they arrived at this model? Just not from the pen and paper. They have done a lot of measurements in the environment and everything, different scenarios, different. I think we have discussed in the previous presentation. Okay, different scenarios, and then they followed different materials, different dielectrics and everything, like different walls and mirror and everything, how it scatters. So a number of thousands of measurements made, and then based on that one, they mathematically formulated that okay, this scenario will be like this: urban, suburban, rural, and highways, and multi-storage buildings. So different things are being incorporated in this model, and then it's not a single man research; it's a multidisciplinary research, and also huge number of scientists and engineers and researchers being involved in this while developing the one particular model. Okay, so now we'll go for next we will move on to the conducted measurement setup. So as we saw the overview of the different components involved in the measurement setup, now we will go in detail. Conducted measurement. Conducted means what? There will be it is not the air medium, it is conducted medium, that's all. Okay, so that's the meaning of you will have a specific cables are connected everywhere, it's connected, so that's what we call it as conducted mode. Okay, so what you can see is, you can see here it's a network emulator, and these cables are being connected. You can see here through splitter you are connecting to the device. This is the device under test, mobile under test, and you are connecting, see, these many cables through splitter or combiner, and then you are connecting that with the mobile. Okay, so then you are measuring whatever things you want. Okay, so what it says, so what is actually being emulated? Okay, that way we can see, as you can see here, just now we mentioned. So what is in channel and all, how they emulate? Interference, noise, Doppler shift, multipath, fading, and everything is being tested. So in this scenario, how UE will behave. Okay, those kind of stuffs being simulated. Here you can see primary cell, secondary cell, and then channel emulator. Then you are adding some noise, AWG noise, and then you are sending the signals to the UE, whether UE performs that or not. Okay, those things and all being verified here. And so you can also check these scenarios like multi-cell handover and mobility. So if you are running in this speed, Doppler shift obviously will come into picture. Okay, so if you are running in this speed and you are having this fading, so fading will happen, right? So because you are moving in a faster manner, and environments are keep changing in seconds level. For example, if you are going in 500 km speed, then per hour, then Doppler shift will come into picture. For example, okay, and you will fading scenario also will keep on changing. Okay, and so will keeps on changing fading scenario, and many things will be keeps on changing. So in that case, what happened is so those kind of stuffs being emulated here, and then you are testing with that emulation. Okay, and you can see that different channel scenarios can be done. And so these are all some of the measurement setups you can see here. Okay, so you are connecting your device and then verifying, validating all the stuff, and so this is similar to that. And so you're sometime now you have to keep your mobile in a shielded box, otherwise what happens is it may be due to the environment, it might cause some problem. So we may not sure that whether it's a real UE problem or environment problem, because in lab we will have a lot of equipments. So due to that interference, it may cause some issues. So that's why it's a shielded box is preferable. And you can see that for a protocol kind of testing, they use simple, radiated. It's a combination of conducted and radiated mode setup. Here, node B will be connected to here, as well as the. Actually, there is two modes are available: signaling and non-signaling modes. So signaling modes, it is real-time scenarios where fully over the air measurements. But non-signaling mode, what they will do is node B will connect it to these antennas as well as the device. Okay, so as well as the device, what they will do, so the device will be put in a certain scenario like After this it has to send like this, these signals. After this so then what response I have to get, that also being embedded here. Then we have to verify those things. So those kind of stuff is being done in the conducted measurement setup. It's mainly for protocol testing and other testing. Okay, next we will move on to the over the air or radiated mode. So now we'll see about over the air measurements. And so before we move on to the over the air or radiated measurement, we will see some of the preliminaries that's to be understood before we go for this. Okay, so first thing is spherical coordinate system. So without this we cannot understand so how OTA will work. Okay, so spherical means this is the spherical coordinate system where there is two axes available. One is pi axis and then another one is theta axis. Okay, so theta axis nothing but, so it is based on the reference only. Say for example, if you are taking xy as the azimuth plane, then it is the xy is axis as the azimuth plane, then it is the phi axis, and z as the xz or yz as the theta plane, elevation plane, it is a theta axis. Okay, so when you rotate along that, then it is becoming theta axis or phi axis. It is a reference based only. Okay, so nothing is there. Okay, then so what I want to say is that, for example, your antenna you are keeping at the origin of the spherical coordinate system, and you are measuring at these points. Okay, like it's a sphere. You consider that inside the sphere, in the origin, the UE or device is being placed, and then you are measuring at these points. Okay, the spherical radial points. Okay, and then you are capturing the different parameters. And rotation will be in general, in conventional measurement we will not take all the points. Okay, a whole sphere. We will take two principal plane cuts. There we used to call it as two principal plane cuts. Two principal plane in the sense, one is azimuth plane, which means your device will be rotated in the xy axis, one rotation. Other rotation is that, okay, you will have theta, along theta you will rotate. Along theta, along z, xz and yz you will be rotating. These are all the two principal planes we used to take, but we will not take cut of this one, like for example in cross. So you will rotate like this. Okay, those cuts and all we don't use. For example, like this. Okay, you can see here several cuts are available, like several rotations are happening along different points. Okay, here actually basically what we are doing is, see, we are fixing how the testing being done is, there are two ways is there. If you are having only one axis positioner, which means it will rotate at a time, it will rotate in one axis, that's all. Okay, so in that case you will fix for example theta as the 90 degree, then you will rotate phi from 0 to 360 degree, that is one rotation. Okay, then you are keeping theta as the 90 degree means what, theta is 90 degree along x axis. Okay, you are mounting mounting a device along this axis. Then if your theta is 100 degree, then again your phi will rotate from 0 to 360 degree. Like that you have to take the 0 to 360 is the one circle, so it's a full rotation. Okay, so likewise you will take. If you are having two axis positioner means simultaneously theta and phi can be varied, and then so that we can achieve in the whole sphere, but it will be too complex because you have to analyze the data, huge amount of data. You will have plenty of points, thousands of points, even lakhs of points. So that we have to see. Okay. Second, this is what is the spherical coordinate system. So in order to better understand, for example, you are having probe here. Okay, you are having your test antenna or DOT, whatever it may be. Okay, now what you are doing is, see, you will have one positioner here, like one positioner means what I mean is it is a rotation device. Okay, you have one positioner that rotates like this. Okay, you can see here that red arrow. Okay, it is rotating like this. You have another positioner here, it will rotate like this, like what is mentioned here. Okay, it will rotate like this. Okay, so two positioner. what I am doing is, see, I am placing one position, this positioner, the particular positioner at one point, one direction, and then I am rotating this. Then I am moving this positioner to other direction. Then I am rotating this. Likewise, I am trying to capture the as many number of points like a sphere. Okay, as I mentioned before, you see, this is the origin of the sphere. Then your sphere will look like something like this. Okay, that's all. Okay. Here we can call it a, see, there are number of notation with the you can find it in the net, or you can find the resources: theta axis, pi axis, elevation plane, azimuth plane, theta polarization, phi polarization, like that. You will have a different conventions. It is a purely x-axis. See, you can start with the x-y axis and the z-axis. That's all. Where you are, in which axis you are going to keep your device, and then what rotation you are going to make, and what position you are keeping your device. That is what is matters. So later we will see that those stuff also. Okay, the spherical coordinate system. Next is that, next preliminary is that we radiation. We always measure at far field distance. So it's a conventional setup. There are near field measurements are available, but they will convert that into, for example, near field measurements are available. It will be something like this. Then you have to near field to far field conversion will happen like this. Okay. So what is near field? What is radiated near field, and what is far field? Okay. See, near field means you are keeping, for example, this is your antenna to be tested. Okay. This is the transmitting antenna. Okay, or receiving antenna. So what you will do, or transmitting antenna, which is known antenna, well-known antenna, whose characteristics is well-known. Okay, you are keeping your antenna here, this antenna here. Okay, then you are testing this one. Okay, what happens is, see, near field, the variation is very high. Okay. Okay, for example, you can see here that the pattern radiation will be like this, okay, something like this. Okay, and also it will have interaction with this antenna also. So that also you need to be taking care. Okay, so then radiated near field is, it is something like in between this. Okay, you will have a see here, it will be, variation will be 1 by r cube. Okay, so 1 by r cube, or 1 by so when distance is increasing, like 1 by even a small amount, 1 meter also will have a lot of differences within. For example, in this region is 5 meter, for example. Okay, within this 5 meter you will have a lot of variation. So if you measure here, you will get one data. If you measure here, you will get another data. If you measure here, you will get a different data. So that's why we normally don't do measurements at reactive near field. Okay, that near field measurement is something different. Okay, those measurements are very carefully measured, and nearby, very close to the antenna, they will capture the field components. Okay. Next is that radiated near field. Here also we'll have variation, but the pattern will starts getting updated. For example, this is the main beam. If you remember the radiation pattern, this is the main beam, and start is shooting up, but it's not here also variation will be huge. For example, here it will be different, here it will be different, here it will be different. But when you are getting to the far field, if you measure here or somewhere else, okay, the pattern looks same only. Okay, that is why we always have to measure the far field at the far field distance, which is 2d square by lambda. Okay, this is how. That's why we always you might have come across far field distance, far field like that. Okay, far field means, see, there is no much interaction between this one and this one. So you will get a pattern at far field. You will get a pattern. It will be a 1 hour lecture, because there are several things are available. I think I have covered a few things in previous presentation also, antennas and RF concepts. So your pattern will be remain same. That's what we have to ensure. Otherwise, what happens is, you will measure in this place. Okay, if you are measuring in these two regions, then your data is wrong. Okay, that's why far field measurement setup is very important. So it will be something like this. So transmitting antenna test, it is radiating, and you are capturing through network analyzer. It is taken from keysite.com. And so in measurement, it's very difficult task. Okay, so we have to, and in our emulation process, we used to emulate like this. Okay, okay, because your two antenna will be there, and then you have a direct wave, and reflected wave, refracted wave. Those scenarios and all we are emulating, okay, in far field distance itself, okay, and those things we have to emulate in the during the conformance testing, okay. Now we'll go to the over the air measurements. It's a basic introduction. As sometime before we mentioned, so you are keeping your device at the origin of the sphere, okay. You are measuring like this. See, you can see here an antenna here, for example, measurement antenna, and link antenna, beam steering. So your beaming, your mobile is, for example, basically, in MIMO, sorry, 5G massive MIMO, the basic measurement is that it's beam steering. We have to find out the where is the beam exactly, and whether it is steering properly or not. Beam tracking, beam refinement, so many tests we will be doing. So here you will have mobile here at the origin. This antenna is at the radius of the radial outer boundary of the sphere. Then you are rotating like this, okay. Or sometimes what happens is your UE will be rotated, but this antenna will be remain same, so that you can find out how it is behaving UE. Okay, this is how it will look like. Next is that in 5G we always use dual polarized antenna, okay, because as in 5G OTA beamforming I have covered those things, okay. Dual polarized antenna. So dual polarized antenna, how you will test it? See, these antennas will always have this test. Conventional test antennas will be having dual polarized. So you can see here this it's a quad ridged antenna. So one ridge will be in vertical polarization, another ridge will be in horizontal, another pair of ridges will be in horizontal polarization. So you will have two connections. When you are connecting this, it will activate horizontal polarization. When you are connecting this, it will activate the vertical polarization. So there are switching mechanisms available, switching unit is available. For example, in UE node B, see, for example, C1 is connected, okay. Now what is connected? Horizontally polarized is connected. In next run, for example, I want to test in this port vertical polarization, means the switch will automatically connected here, and then this switch will be connected here, and then you will get this, okay. So it is a dual polarized scenario. Next is that, so any setup for that matter, before you move on to the measurement, you have to calibrate, okay. The calibration, how it is done, it's very simple actually. See, this is the path, for example, this is the path, okay. This is the path of measurement, okay. In this, instead of connecting to the antenna, what you will do is you take that connector and then connect it to the vector network analyzer, okay. You see, for example, you are here, okay, and then you are connecting to the vector network analyzer. So now what you can measure? S21, okay, S21. So if you measure S21, so what are all path losses occurred in this circuit is can be found, okay. So those things need to be compensated. Otherwise what happens is, for example, you are straight away connecting your antenna and testing, okay. That time what happens is, for example, see, you are getting some 10 dB of gain, okay. For example, 10 dB power, okay, for example 10 dBm power, okay, plus 10 dBm power. But actually you should get 15 dBm power plus 15 dBm power. Why? Because why you are getting 10 dBm power? Because you are not compensated this path. Okay, for example, this path is offering 5 dB loss. Okay, so that we have to find out in the calibration stage. Okay, so what you can find is, see, you are sending your power. S21 is what? Our output power divided by input power. Okay. Output voltage, or if you call it as voltage, then it is output by input. So output power is like, this is the output power, this is the input power. Okay, if you take the ratio, you will get the difference, that okay, what you are sending, what you are receiving. Okay, then you have to compensate those things. Then once you are, compensation means what? In your setting that, say, for example, if you are getting plus 15 dB, 5 dB, then you have to compensate. When you are doing this measurement, then you have to add plus 5 dB compensation, path loss compensation. Then you will get the plus 15 dB. So something like this. Okay. So this is how you have to compensate. Calibration is very, very important. Otherwise, you will end up in getting wrong results. Okay. That's why it is you have to take it very seriously. We have to take it very seriously. Next is the OTA testing. So yeah, I think these are not all we have covered. For example, UXM and PropSim. This is channel emulator, and then channel emulator, what it emulates? You can see that, as I have mentioned before, it's emulating building scenario and trees, towers, and home, and these things, and multi-storage building at home, and also electric power, electric lines, high power electric lines. So everything is being simulated here. We have mentioned already. So then, so you are connecting with this, then you are keeping your UE within this shielded box and OTA measurement setup. Then you are you are applying these scenarios, and then see you are sending this signal from the node B, and then you are applying these scenarios, and then see how UE is behaving. Okay, those things are being measured here. Okay, and as I mentioned before, it should be in ideally it should be at far field distance. Okay, measurement at it should be done at far field distance, and so the amount of the distance your test zone. So we will be discussing about quiet zone also. Okay, you are keeping your device, and then you are having measurement antennas. Okay, test observer antennas. So what you will do is this UE, what we are in transmit mode and receive mode is there, that we will see later. Okay, then you are measuring, okay, all this stuff. Okay, this is one kind of setup. This is another kind of setup, like channel emulator or probe antennas, and then measuring all these things. Okay, next is that, see, in your mobile, it is, you can see that, so you will have get different type of beams that you have to capture through these antennas. Okay, and so beam sweeping, ideally this beam sweeping will be happening like this. So you have to capture where exactly the beam exactly, so that you can find, you can verify your algorithm as well. Okay, for example, if you are activating the beam to be directed towards, for example, 15 degree, for example here it is fourth number and beam number 4, you are activating, but you are not getting that any signal in that direction, which means you are having some problem in the algorithm or device or components. Okay, then what you can do is, for example, if you are getting 3, then you have to adjust and then see what went wrong. Then you have to debug this issue. Finally, you have to ultimately you have to get, if you are activating for fourth beam, then you have to get fourth beam. Okay, like that. So these are the chambers. I think we have discussed already. So chambers, you can see here, this is the sphere origin. That is what I meant about. Okay, this is the sphere origin. You can see that at the radial of the sphere, you can see that this many antennas are being mounted. So it will capture. So for example, your beam is towards this direction, then you can get the signal from this. Or if you are transmitting from here, then it has to receive it properly, which means your beam is directed towards this. So there are beam refinement, some measurements are available. Before we move on to the any testing, we have to do that. That also we have to see, and that I think I will cover in next presentation. Okay, so beam refinement search. Once your beam, you are ensuring that beam is everything, then you can go for compliance testing. Otherwise, it is waste of time. Okay. I think this we have mentioned already. See, this is how it will look like. So azimuth, you can rotate like this, you can rotate like this, and elevation you can rotate like this. Okay, you will keep in one position, for example, one position, then you will rotate this antenna, then you will keep in another position, then you will rotate this device. Okay, then you will keep in another device, another position, then you will rotate this one. So this is how it will look like. Okay. Now the quiet zone, it's a quite important parameter. So size of quiet zone is nothing but, see, quiet zone is nothing but, for example, you have a device. Okay, if some equipments are nearby, then what happens is it may disturb the radiation performance or any performance RF performance of this device. So that happens is, then if your beam is not, for example, sometime beam is going like this instead of here. Okay, so it may be due to the real hardware problem, or what happens is it may be due to the near surrounding things. So that's why we have to ensure that quiet zone. Okay, quiet zone is nothing but, it's nothing. See, depends on the say quiet zone. See, it is simply there is no disturbances. So quiet zone means there is nothing is available. Okay, then there is no radiation or any RF signals available within that region. Okay, there only you have to keep your mobile. For example, you can see here, depends upon the size of the DUT, because it is saying obviously, because if the size of the DUT is huge, then the quiet zone should be ensured. Okay, that nearby that, see, for example, your device is you have to keep your device at the center of the quiet zone or somewhere else. Okay, then you have to ensure that this radius, there should not be any obstacles, it should not radiate. Okay, what they will do is, in general what they will do is, you will have a positioner also will have impact on that. What they will do is, positioner also they will cover with the anechoic chambers and the absorbers. Okay, so that it will not cause any problem to the DUT. Okay, and for example shall be sphere of radius for example 7.5 centimeter. Okay, and tablet type of devices, because it will be huge, that's why 15 centimeter. This is the spec it is given, but different labs will follow different quiet zone capability, because ensuring quiet zone is very difficult. Okay, actually, because you have to do multiple measurements and to ensure that the quiet zone is proper or not. Okay, that is a different story. When you install the anechoic chamber, they will use to check quiet zones as well, because so it is it is being mandatory, but it is being mandated by test system, because certification, if you want your lab to be certified lab, then you have to ensure this quiet zone, because otherwise it will be if you are installing anechoic chamber, the quiet zone performance will be ideally measured. Okay, how they will do is, see, they will have a antenna here, measurement antenna, and then they will keep some device here. Then they will see both devices are known characteristics, both devices with the known characteristics. Then they have to get the expected results. Otherwise what happens is, you will due to some disturbance around that, we are getting that deviation in the results. So that we can ensure that, okay, quiet zone is not proper, then we have to do the mitigation process. See, for example, you can see quiet zone, any positioner or support structure, so these can disturb the quiet zone. Okay, so that's why it is decided based on the size of the DOT and this structure. Okay, so quiet zone is center of the rotation of DOT, and then surrounded, zone is current surrounded by that particular one. Okay, you can see the variation may be in different line of sight links, so different things are happen. Okay, next is some of the measurements. Okay, so some of the measurements are beam acquisition tracking, beam refinement, beam feedback, beam switching. So these are all we have discussed already. Algorithms, beamforming network and everything. These are all the these are some parameter maybe on benchtop itself we can do it, but some parameters we may not do it. We have to do it in OTA itself. So the polarization we have to ensure, bandwidth, beam width, beam squint, ARP, TRP, everything we have to ensure. Okay, TAS and everything. So these are side lobe level and all we will not measure in the OTA, because these are all already been measured in the, these were antenna characteristics. This has been separately measured. Okay, efficiency, correlation coefficient. This is the different process. It's only for antennas to ensure as a system level. Once you are integrating antennas with the system, then you will measure all these things whether you are getting properly or not. Okay, that will be, it can be done in a normal setup also. Okay, so I was mentioning that beam acquisition tracking. See why? Because this is to be measured carefully. What happens is, for example, you are receiving in this direction. Okay, you are receiving, for example, DOT antenna is receiving in this direction, but your antenna being tested, right, it is directed, physically or mechanically it is directed towards this, but electrically your beam is like this, something like this. Okay, so here what you are sending is, you are sending null, you are not sending any information, you are not sending signal to some other direction. So that's why we have to refine the acquisition tracking. You have to refine the beam, beam refinement, some beam search process. Initial beam search process will be done before we take up the measurement. So in order to ensure that it's this we call it as beam squint. Beam squint. See, actually, it's mechanically it is placed like this, directed towards this antenna, but electrically your beam is something like this. So it is being squinted. Okay, so that's why we call it as beam squint. So then we have to electrically adjust so that this beam is something like this. Okay. Next, there are different measurement methods are available. One is direct far field methods. Other one is indirect far field methods. The near field to far field conversion. Okay, that far field method I have mentioned. So you have to keep your device, both the device test as well as the transmitting device antenna is as with a distance of 2d square by lambda. Indirect far field is, it's a compact version of far field distance. So by employing the cutter and a compact antenna test range that we will see in the next upcoming slides. Near field to far field. Okay, it's a compact setup, and then probes are used to capture the field components. So with that components, they will extract the far field parameters by employing different algorithms. For example, FFT or FFT. Okay. So direct far field will be looking something like this. Okay, you can see here your duty here and antenna is at some distance, which is probably 2 d square by lambda distance. So it will be something like this. Okay, and so quiet zone we have discussed. The quiet zone radius is this. So you have to keep your device within that quiet zone, and so that your disturbance is not due to any nearby obstacles. And then you are measuring at this point. Okay, you will have a positioner, and then you are rotating like this. For example, you are rotating like this, you are keeping your device in this quiet zone. Okay, and so these are all some of the path loss calculations. I have mentioned that we have to calibrate the setup before we move on. So for example, your DUT size is 5 centimeter. Then at this frequency range, so near field or far field boundary is 47 centimeter. Then path loss will be approximately this, and frequency 100. It will be boundary will be different, and then the path loss will be different. So this is a rough estimate they have made. For example, if you are measuring in your system, then you have to ensure this approximately this path loss. This path loss only should be there. It should not be too much. Otherwise, what happens is you will end up in getting wrong results. Okay, that's why they have given as a reference. Okay, if you are setting, for example, you are setting up a lab to test 5G devices. That time you have to ensure these values. Okay, minimum criteria. Otherwise, they will not certify your lab for this testing of 5G devices. Next is indirect far field. It's quite interesting. See, it is from concept of reflector. Okay, you might have seen parabolic reflector. You will have feed here. Okay, so it will radiate like this spherical wave. Okay, then for example, it's a spherical. I'm sorry. Assume that it is a spherical wave. This is the reflector. Okay, this is the reflector. Okay, and so you are sending this. Then what happens is you are sending the signal, then it's get reflected, because you are sending for example, you are sending the spherical wave. Your reflector shape also almost spherical in nature. What happens is it will compensate the phases, because this is arriving early, this is arriving late. So here what happens is it will get reflected from here. This will become this total entire thing will be compensated. At this point it will be a planar wavefront. Okay, so the main disadvantage of this is called as center fed. Okay, if your feed is here and then you are having a reflector like this, and then if you are having this center fed, this is called as center fed. Okay, center fed reflector. The main disadvantage is that, see, when it gets reflected, right, okay, with a plane wave, it's get blocked, or it is the blockage will be there due to the feed. So that's why what happens is what they have done is that you have feed. Okay, you have this parabolic reflector. This is the origin of the parabolic reflector. Okay, then you are having this origin. What they will do is, so till this point only it is getting blocked. Okay, till this point only. Okay, till this point, see some of the point it is getting blocked. What you can do is, see, you can avoid this, you can cut down these things. Okay, then your feed, you can rotate your feed towards like this. Okay, then what happens is you will have something like this reflection. Okay, plane waves. Okay, so this is how it's called as offset fed reflector. Okay, so this is how it is being done. Okay, so what you are doing is basically, see, you have a parabolic reflector. You have, for example, if it is center fed, okay, it is being reflected like this, like this, like this. Okay, you are only taking this portion alone, and then you are rotating your feed towards this direction alone, because because if you keep your feed in this direction, what happens is most of the energy, after almost 50% of the energy, is wasted here. That's why you are rotating this feed like this. Okay, then it will be hitting on this, then coming back like this. Okay, so this is how it will look like. Okay, that's why. Okay, so this is the basic principle about behind this compact antenna test range. Okay, it basically comes from a reflector. Okay, and so it basically comes from reflector. From that only this derived compact antenna test range. So you have a feed here, then it gets reflected like this. Okay, and it's like this. So you are keeping your device, it can be rotatable like this and rotatable like this. So based on that, positional controller available, a system simulator, and then you are measuring all this stuff. Okay, next, these are all measurements can be done, different measurement techniques. And here compact antenna test range, range means what? Distance. Okay, the whole size of the thing, this is the distance between your DUT and test antenna. It is depends on quiet zone, because you cannot have your reflector here, because it will affect the quiet zone. And focal length is nothing but your this is the focal length, this is the focal length. Okay, from the feed to reflector, what is the distance? That is focal length. Offset angle, so what angle you are offsetting. For example, you see this is the offset angle. The next is feed location, so where you are keeping your feed, where you are keeping here or here, you are here keeping here or here. So that also matters. Based on that, this range will be designed. Okay, next is that calibration. As I mentioned before, calibration will have to be done. Okay, so same thing, you have to connect to the network analyzer. Instead of connected to the system simulator, you will connect to the network analyzer, and then this you will connect to the directly to this antenna. Okay, instead of positioner, okay, directly connect to the antennas. Okay, then you both are connected, you have to measure the S21, then you can calculate the path loss in this path, then you can do it. Okay, next is that this is the ray diagram, ray optics, like I think you can use the some of the softwares like Tikra. There is one software is there. In that software you can able to find out ray optics as well, ray diagram. This is called as ray optics method. Okay, what they will do is how this is being transmitted and then received. So this is the device under test, and you are having feed here and you are having reflector here. This is how it will something look like. Okay, then it is another way of representing radiation pattern measurement. For example, if you are measuring the radiation pattern of this is method 1. For example, TX as DUT, TX by when TX by DUT. Okay, DUT is transmitting, DUT is transmitting, and then you are being received by the see reflector has two functions. One is when you are from the feed, it gets reflected as a planar waves or collimated waves. Okay, when the collimated waves arrives at the reflector, it will focus the beam in to the feed. This is what the principle you might have seen in the dish antenna. This antenna is something. This antenna is same thing. Okay, so same thing like that. Okay, next is that this is a quiet zone. Say this is what I'm mentioning. So offset angle, and this is the focal length. This is the vertex, means what in the center of the parabolic reflector, and the quiet zone and everything. Okay, this is how this is the reference they have given. So if you are having this much, then you can select the range as well. Okay, working example. So you can see here focal point to this one, you are getting planar wavefront or collimated wavefront. Okay, and this is the parabolic curve. Okay, these are all the observers is available. So this is how something look like. Okay, so you can see here quiet zone and this reflector. Okay, so one more thing is that you cannot use simply reflector. You have to go for a serrated reflector. Why? Because for example, you have here antenna. Okay, so when signals touch the edges, okay, when signal touch this edge, what happens? You see, there's one principle. When a wave touches the edges of the metal, what happens? It scatters like this. It scatters like this. Okay, so sometime what happens is it will come inside also, inside the region also. So and this will cause the problem with the actual test environment. Okay, it will disturb the, for example, this scattering, this scattering, different scattering will disturb the test environment. Okay, so that is why we go for serrated one. What they will do is, see, it's a serrated means it's a gap is there, right? Gap will act as a capacitor or inductor. So this will act as inductor. So capacitor and inductor, what they will do? It's a storage devices. It will absorb those waves. It will not affect this path. So it will either absorb or cancel the reflection, scattering, or in other words, it compensate the scattering, and you will not have feel the scattering effect. So that's why they go for a serrated kind of compact antenna range. You can see that in many of the pictures. You can see only these kind of things, okay, because serrated is preferable. Otherwise what happens is, whether you are getting the disturbance from the UE or the environment or reflector, you may not be knowing. That's why they are always going for this one, okay. Next is that, see, this is the indirect far field, okay. I just want to mention. So you can keep your device here. This is scenario 1, or you can keep your test antenna here, okay. So you can keep your device anywhere, okay, in this quiet zone or edge of this, center of this quiet zone or edge of this quiet zone. So this is the two scenarios is being followed. Here your device is radiating, and then it is getting focused at the focal point, that is horn antenna here. And this is another scenario, like it's RX test cases. For example, RX test scenario, your horn antenna will radiate and the device will receive. So how it is behaving, that the receiver end, scenario 1 and scenario 2, okay. And you can see here. So the position, I think we will discuss in some time. Okay, next slide or so. Okay, so you can rotate where you will keep your device. So you are keeping here. There are multiple scenarios can be followed. Okay, you can keep your device here. Here they have kept our antenna, but you can position 5, position 3. So like that, several position can be opted. Okay. So this is the near field to far field method. Okay. Near field means you have antenna here. These test antennas are being, test antennas or transmitting antennas or receiving antennas is being kept at a near field. You are capturing all this information, like then you are converting back to the far field pattern, as we mentioned before, by employing several algorithms. So we'll continue with the near field. So here actually see, near field means you have duty here, and then these antennas are in near field. So previously we saw that, right? Reactive near field, radiating near field, and far field. So we'll keep in the reactive near field, radiating near field. Then we will capture all those informations, and or in some measurements, what we do is we closely, in near field measurement, we closely, we'll place a probe very near to the device in order to see whether a signal integrity problem is there or not. Like mutual coupling and coupling between these two components in the circuit. If you are having very big structure, then you cannot move often. So that's why they go for this near field measurements. So there you can find out many signal integrity problems, EMC problems, and radiation problems. So many characteristics can be found with the new those kind of near field measurements. But here it is not very close to the one. So it is, you can see here, this is in this only these antennas are mounted. This anechoic chamber, in this absorber, these antennas are covered by these absorbers, because and at this point, you can see that the mouth aperture of the antenna will be there. Okay, so here why we are covering with the absorbers, because we have to ensure the quiet zone. Okay, because it should not disturb the the performance of the device. So that's the major reason. You can see here there is another set of design. Okay, they what they made. And one more thing, if you want to calibrate the setup, okay, so you have to find out what typical path loss is available. Okay, so path loss, how we can estimate? It is very simple. See, what we can do is, see, for example, if I have to find I can just mount these antennas and then find out what is power received. Okay, so what we are doing is, source is there, then you are sending the reference power. So some power you are sending, that very well, and the gain of this antenna is known. So what will be the power at this aperture? It is P reference power plus gain. Okay, gain of the antenna, which is actually product of these two. In dB we call it as P refer plus Z refer. Okay, and you are receiving this using this antenna, measurement antenna, and you are receiving this power. For example, your intercepted power is this much. So from this we can able to find out this gain of this particular antenna. Okay, you know these parameters, you are receiving this much power, then what should be the gain? So like that we can able to find out. Okay, so and so if you want to find this gain of this antenna, you can find out. Or else if this gain also known, then what is the path loss? So if this gain is known, this is known, this is known, this is known, then the actual path loss happened in between can be estimated. How we can estimate? P iso minus P test. If you put, okay, then what will be the value? So the difference is the here I assume that P test is equal to what power is received here and plus gain. Okay, now if you subtract these two, then you will get the actual path loss in the path. Okay, and so now we have to see, I think we mentioned during spherical coordinate system, DUT rotation. So what way we can do it? So the standards are recommending certain rotation position, but that is the obvious one. So you can see here, you can keep your mobile device along a z-axis. Okay, z-axis, and then what rotation is possible? So you can see here, you can rotate like this, and then like this, and see 3 kind of rotations you can make. So any kind of rotation we can make. So like this along z, with reference to z, you can rotate, so that you can cover entire sphere. That is the major idea here. Okay, and you can keep your device like this. So you can keep any rotation that you want. This is the reference they are giving. So you can see here. So mobile we kept like this. Then you can keep the earphone at the bottom, in the top, or you flip the device and then rotate all these 3 axes. The another type of rotation is you can keep your device along x-axis and then do all those combinations. Similarly, you can do it for you can, by keeping the mobile or device along the y-axis, and then you do all these rotations. Okay, this is how they rotate in order to achieve the over their measurement, like in the entire sphere points. So now we have to see what points we are going to measure. Okay, because you have limited number of antennas, you are not covering entire sphere. That you remember, you are not covering the entire points of this sphere, because that we cannot cover ideally. Okay, what we can do is the maximum best and possible in the sphere we will capture the capture the thing, and then we will estimate the radiation or total radiated power or EARP, whatsoever we will calculate based on that one, those data only. So now this is another type of, so now you can see, you can have better feel, because here only device was rotating. Here you can see this is the test antenna. See, this is the distributed axis system, which means you are rotating your test antenna as well as the device. Okay, this is a position another 2. Okay, you can see here, you can rotate these 2 and then rotate. The other one is a combined axis system. So combined axis system means, which means you are rotating only your device, not the in compact antenna test range. See, this can be done even conventional test setup, like you can rotate your test like horn antenna like this. Okay, and simultaneously you can rotate this UE as well and capture the power whatever you want. Okay, but in catheter chamber you cannot implement those kind of thing, because this will not be movable, because this is fixed one. Okay, catheter chamber, this once this is designed, and it is designed, that's all. You cannot alter this one. If you alter, then again you have to calibrate the setup. So that's why we have only option of rotating the UE, that's all. Okay, due to orientation 1, orientation 2. Okay, you can see here like top bottom, just you are changing the top bottom and then rotate like this, that's all. Okay, and you can see here reference AAT measurement distributed axis system, as you mentioned before. This is another way of looking at it. So this is the positioner. Okay, positioner also you can rotate in the azimuth direction, and you are rotating this horn in elevation direction. Okay, in the sphere you can see that this is the sphere. For example, if you assume that 2 principal axes will be like this, so this is called as azimuth plane and this is called as elevation plane. Okay, so theta, in theta the elevation means what? Theta plane, and azimuth means what? It's a pi plane. Okay, so you are rotating you are rotating your device in the azimuth plane rotation, and then you are rotating your horn antenna in the elevation plane, so that you are covering the entire sphere. Okay, that's how it works.
Okay, but in combined access system, so if you are employing the scatter chamber, then you cannot have both you cannot have both the horn antenna and device can be movable. So what you will do is you will only move this alone in both axes. Okay, here the flexibility is that both the axes, that is the flexibility. Okay, you can see that. So azimuth as well as the elevation, you are rotating your device, that's the thing. Okay, and you can see here that P1, P2, P3, P4, P6, so these are all the location where you can keep your device and then measure. Okay, rotate all these things, so that you can cover entire sphere, that's all. Okay, that's the idea over here. And distributed access system. So this is another picture what we have. Okay, combined access system and distributed access system. Now, so just now I mentioned that we cannot measure entire sphere. The sphere I meant is this one. Okay, so you cannot measure each and every point. Okay, each and every point. So in that case, what happens is, so you cannot have a each and every point. For example, you cannot have each and every point measured. Okay, and so in order to avoid that, so you cannot measure each and every point. So in order to avoid that, so what you can do is, see, there are researchers have done several research and then found that there are two kind of grid points. Grid points means, I mean that which point you are keeping your we are observing the capturing the data like a signal from the DOT, or transmitting the signal to the DOT. So those points are one way is you can just in each pair you can cut the sphere as one slice, and on the top slice, next slice on the circle. Okay, on the circle you are placing these points. Okay, and the next slice you are saying on the circle you are placing these points, and the next circle you are placing these points. So that is the one way. Other way is that it is like a kind of mixed. Okay, so the another slice is like this. Okay, it like this, it will look like this. Okay, so this is another slice. Okay, so these points, if you put your antenna, if you capture the data, then you can able to measure. So how many points are there? 266 unique points are there, and so 266 unique points are available here. What they are doing is, in phi plane and theta plane, they are keeping your device, capturing the power at a 15-degree interval. Okay, which means you have your device. Okay, you have access here, x axis, y axis. So at each 15-degree, so this is the 15-degree, at each 15-degree you will have one point. Okay, you have to imagine it is 3-dimensional, so you have to each 15-degree. So the difference between this point and this point will be 15-degree. Okay, and similarly, so this is how it will look like. For example, if you are so in this point you are capturing this much data. Okay, it's kind of cell coverage. Okay, cell coverage. Finally, you are doing what you are doing is you are integrating the whole data to get the, for example, total radiator power, EARP, whatever you want to calculate, combined difference, distribution function, whatever you want, you can calculate. So by integrating these values, so you are capturing the signals at each point or field components. Okay, and if you EM point of view, it is a field components, then you are integrating all those values and all those components and then finding out the radiation pattern. That's what is the idea. Okay, if you are measuring the antenna perspective. Okay, then you are calculating, these are all the, then you are calculating the derived parameters like gain, EARP, whatever you want, you can calculate. So that is how it will look like. Okay, so you can see that these mesh points are here. So you are measuring this point. Okay, you can see that this, for example, if this beam is activated here, it is showing dark pink color. Okay, if this beam also activated, so here it is not activated, something like that you can assume. Okay, so if your beam is in this direction, this will have a certain orientation in both phi axis and theta axis. Then you can define that okay, your antenna is radiating in this particular direction. Now you can have an idea that okay, how do we ensure that beam is pointing towards particular direction. This is how we ensure that. For example, on this grid only I have to get the results. For example, if I am pointing this beam towards this. Okay, so similarly we can find out for others. So you can see that at this point there is a huge, for example, if the pink has the large intensity, then pink has a very large intensity compared to this one. So this is how we have to make out that beam is measured in the particular direction. Okay, so you can see here there are very good explanation is given. 38,810 140 measurement points on left, so with the 3 measurements right. So like that, you have to measure so many points in order to get the accurate results. Okay, so this is the 140 points, measurement points. Okay, so it is like it's a scattered one, distributed one, whereas here it is to 3000 points. You can see the sphere is very small mesh shells, grids are there. Okay, so but implementation cost is much expensive, hardware complexity, everything will go shoot up, but the accuracy of the result will be somewhat better in this case. But here it is, accuracy may be compromise, but cost wise, implementation wise, and then physical realizability wise, it is far better than this 3000 points. Okay, so but those who are expensive labs has this kind of thing, but some of the common labs will have basic requirement testing, then they will have this kind of setups. Okay, next is that, okay, this is how it will look like. For example, if I am putting my device in the near field measurement setup, so my beam is towards this is one beam number 1, this is beam number 2, this is beam number 3. Okay, so I have to get the signal at respective antennas, otherwise what happens is there is a beam has some problem. Okay, this is how I have to measure. So these are all the grid points are there in the sphere. So I have to get, for example, if my beam is pointing towards this grid point, I should get maxima in this direction, not in this direction or anywhere. Okay, so this is how we have to find out typically beam forming can be found in this, and also beam research, beam peak search. See, beam peak search we are doing, and then refinement, be coarse fine. So there are different kind of searches there. One is coarse search. What they will do is they will sweep randomly 3-4 antennas. For example, in this, out of this, they will activate some of the antennas and then see which direction is the beam. Then what they will do is they will do the coarse fine search. Okay, fine search. So one for example, beam is now you can see if you do coarse search, you will receive the power here. But if you do fine searching, which means what? Fine means what? Coarse is like you are measuring here and here and here like this. Okay, and but fine search means you are measuring each point, this point, this point, this point, and this point, so through this antenna. So all the points you are measuring and then deciding where is the exactly the beam peak. Okay, that is the fine search. Okay, coarse search will have to have that information. For example, you will measure only this point and this point. You may miss this beam maximum because the maximum is here, but you are not measuring there. So in that case, what will happen is you will misguide the you will end up in getting beam peak direction may be different. So in that, in order to avoid that, they are going for a fine search. Okay, fine search means it will measure in this point, this point, this point, so all these points. Okay, so all these points are measured, then they will decide, okay, where is the peak beam peak available. Okay, so that's how they decide the beam peaks. Okay, so these are all the some of the measurement technique procedures is mentioned in the spec 810. You can have, if you find time, then you can use read that one. First step is select 3 alignment option. 1, 2, 3 we have seen, right? So those alignment option you can, for example, device mounted along x-axis, y-axis, or z-axis. So that diagram we are already shown. So you can mount on that. Then reposition TX test cases, RS test cases, which test case you are going to test, that you have to ensure. Then you can see here theta you are rotating this much and phi you are rotating this much. So like that you have to rotate and then see which option you are going to opt for. Okay, then connect the simulator to the DOT, then find out first you have to do is, what we have to do is we have to find out beam peak direction. Otherwise respective polarization to be ensured before we go for measurement, and peak beam peak also to be ensured. Okay, once you are upon ensuring those things, then you can go for other testing, kind of testing. Okay, and so mean power is it's a calculation one, so that the code will take care of. Okay, and then from the spectrum analysis, power meter, G-node emulator, so we will capture all those power values, and then we will have to background, we have to calculate the whatever the parameters required. For example, AARP, you have measured will have two kind of polarization. One one polarization will have one value and another polarization will have another value. By combining these two, we have to find out the cumulative EIRP or final EIRP. Okay, and similarly TRP measurement procedure is mentioned. Okay, similarly you can here peak EA effective isotopic sensitivity measurements. And okay, so this is another measurement setup where we not use much antennas. Here actually it's a kind of a resource management testing, radio resource management testing. So there we mostly protocol will come into picture. So these kind of antenna structures will be in order to emulate. See, one cell is here, another cell is here, another cell is here, another cell is here. How it is reacting. So some kind of testing they will do. Okay, in this with this setup. Okay. So that's all. So thanks for watching, and we have what we have covered is what is device validation introduction, coordinate systems in an elaborate manner, and different measurement setups, conducted and radiated basically. Radiated, and different measurement methods, direct far field, in NFTF, and different rotation, different UE positions, what we can do, and various parameters. How do we measure that, and what beam peak search is about. What is the grid points? So many things we have discussed. Some of the measurement procedures, some of the parameter measurement procedure for the each parameter. So those things are already covered. Okay. So thank you, and if you have any questions, please post here. Okay. Thank you very much for your time and your support. So if you have any feedback on my presentation, please do post here. Thank you so much. Bye bye.